maybe a quick advertisement for a book that I don't know should have been out since 2 years but isn't out yet. Andrew wrote a book about the process of engineering machine learning solutions. So this book will have, when it finally arrives, 100 chapters. Every chapter is roughly a page long and addresses a specific problem, like where do I find data? How can I label data if I have too few data? It's really interesting, very practical, not very in-depth technical. It's also something you give to a manager of machine learning engineers to understand how these kind of people should be led. So will probably be a very interesting book with lots of practical tips. There's a website called machinelearningyurgen.com org, I don't know. You can subscribe there for a mailing list and you will get a notification if it comes out. You can also download draft chapters that are not finally layouted but basically have the content. So that's a good resource for practical machine learning. So what we will do now, do machine learning from scratch. And I will try to, no, we will make it in time today. Can somebody give me a sign when it's just 5 minutes to the end? So I can, when, if you don't know when the end is, I don't know it. When is it?
3 p.m.
Probably in half an hour, right? 35 minutes, something like that. So can somebody tell me at 2:30 that it's at 2:40 that we should basically come to an end? Okay, but we will try to highlight the points. We'll make it quite condensed because you know already some things about it, but we will try to highlight the points that are important here. Machine learning from scratch, meaning without any libraries. Sometimes if you too quickly start using very sophisticated libraries, you might miss very important points in the field. And this lecture is basically to see if there are any such points you need to pay attention to. So we are again, and for the rest of the lecture we stay in the example of the carbohydrates that we want to know how much energy is free when we burn them, and we want to build a machine learning model for that. We want to do it with a straight line because it looks not too bad as a first thing we could do. We'll look into all the details, like into every relevant math and Python line to do that, and we'll do that without libraries. So how do we do that? First thing is, let's analyze that plot. We have all the points, let's place a straight line fit in it by hand. How would we come up with the parameters of the straight line by hand? We would probably do the thing we learned in math and try to estimate the gradient by seeing, okay, 1 point here, 1 point here, calculating the difference and coming up with a gradient of roughly -50. So we know the gradient of the thing, and we also know from school back in the days that if we have the gradient and the y-axis intercept, we have all the parameters of the straight line that exist. So we know everything about the straight line in 2 dimensions with the gradient and the y-axis intercept. So there are 2 parameters we have to find out, and we just did by eye, gradient and y-axis intercept. What we will do now, design a machine learning solution and program it that does the same thing for us. That's the idea. So our conclusions are, we have labeled data, we have the correspondence of number of molecules to energy release, so we can do supervised learning. We want a continuous valued output, and I don't see too much value in binning here, so let's do it as a regression task. Straight line seems to be reasonable, let's do it with the in favor of linear regression as a first thing. That will be our plan. So, we started the lecture today by stating that machine learning is representation plus optimizer plus performance measure. So, how do we represent our hypothesis H, our straight line? How is it represented? First mathematically and then later in code. Our hypothesis function is always a function of our input data x and a vector of parameters. This would also be the same if that would be a neural network or whatever kind of decision tree or whatever. But how does it specifically look like if we want it to be a straight line in 2 dimensions? And it looks like that, the typical form of a Geradengleichung, of the equation for a straight line. Theta 0 plus theta 1 x. Y-axis intercept times plus gradient times the input gives you the corresponding output, the point on the straight line. This we probably learned in school lots of years ago. Why do we call these things theta 0, theta 1? This is just how you usually do it in machine learning. These things are either called thetas or weights. W, here we adopt the theta. So, that's an equation for a straight line. What? Theta 0 is intercept, theta 1 the gradient. Of course, you already know, if we change these parameters, we change the thing that defines a straight line. So having different values for the theta 0s, theta 1 corresponds to having different straight lines. And what we want to do is find the right one. How do we want to do it? Put in our training data and the corresponding from our data set labels into a training set, into a learning algorithm that infers these 2 parameters. From the examples, we want to infer specifically these 2 numbers, which is just a concrete example of the same stuff we talked about last week. So, we know how to represent it. That's the representation of our hypothesis, the straight line equation. So how do we choose or find these the values, the best values for these 2 parameters? In order to do that, we will define a thing called a cost function. Sometimes also called loss function, sometimes called objective function. We need a function by which we measure how well we are already doing, and by optimizing this secondary function, we'll basically be better on our task. So our task is to choose these 2 parameters so that the results of our hypothesis function for specific inputs are close to the correct y. This is what we talked about last week. How do we do that? We define that secondary function, this cost function, that is a function of the parameters, and somehow quantifies the cost of errors that we make. I say here the cost of errors, not how many errors we have, because it might be in a different case that some errors are more expensive than others. Think about the terrorism example from earlier today. When we misclassify a normal passenger as a terrorist, this person will be inconvenienced a bit. And we maybe have to pay a recompense of 500 bucks or so. If you misclassify a terrorist as a normal passenger, the cost might be a blown up airplane. And a lot of lives that are lost, and reputation, and also the airplane. It's much higher the cost. So the cost function in general measures the cost of errors, not just quantifies how many errors there are. And that's important, it's a function of the parameters. Meaning, it measures the cost of error with respect to the parameter values. Which implies when we want to, for example, reduce the cost, then we have to fiddle around with the parameters. It means that the parameters are all we need to change in order to change the cost. How does a specific cost function for our example might look like? Of course, it's a cost function of our 2 parameters, the y-axis intercept and the gradient. These are our 2 parameters. And here's an example of what we could choose as a reasonable cost function in this regression set. It's a mean squared error loss function. What does it mean? Let's go from inside to outside. Here in this parenthesis, what do we have? We have a call to our hypothesis function with the current parameter settings. For example, number I out of n. This gives us the prediction of the model for this input example. This is the true value that should come out. So the difference between the 2 is the error. So how much apart is our prediction from the truth? Why do we square?
Sorry. Yes, I don't know in English.
because of the negative sign.
Yes.
Yeah, that's one reason, but we could also do a norm for that, L1 norm Betrag, absolute value. So why do we square?
It's easier to calculate.
Easier to calculate? I know what you mean, but I'm not completely sure that's, yeah.
Bigger errors are weighted more heavily.
Pardon?
Bigger errors are weighted
Yes.
more heavily.
The squaring here means that larger errors are not just linearly represented in the loss, but they are squared. So we punish larger errors more severely. This is so we don't care too much about small errors, but we care much about big errors. This is basically what the squaring leads to. You said it makes calculations easier. I would say we make the square here in order to punish larger deviations, and we put the 2 here in order to make calculations easier later. We will see later that we will have to take derivatives of that function, and taking derivatives basically brings the 2 down here, and then it will just cross each other out. This is why the 2 is here. It has no other meaning than making the math a little bit nicer. And this is actually what mathematicians think is beautiful.
A question about the square error. Don't let the function become convex?
Yes, it does. We will see more about it later. It makes the optimization quite easy. Is that also what you meant?
Sorry?
Is this also what you meant? It makes the function convex and the optimization more easy.
Well, it's one point, but compared to absolute values, it's also easier to compute the gradient. So
Okay.
both factors.
Good. So we have a cost function here that measures the difference, squares it in order to punish larger values more severely, does it for all training examples we have, and calculates the mean of that, the average, and then divides by 2 for mathematical beauty. That's called the mean squared error loss function. Mean squared error loss function. And this is a standard choice for regression problems. We will see more about it next week. Precisely what we want to do now, as soon as we have formulated that function, that is, until now we just formulated it. We have not related it to our task precisely. We will do it now when we want to choose these 2 parameters in a way that optimizes our machine learning problem. We can do this by minimizing this function j with respect to its 2 parameters. And this is what it will do now. And this is what usually a machine learning solution does. We formalize a loss function, we optimize it. We maximize it or minimize it. And this is why I insisted in the beginning that you have to choose the correct loss function for your problem. If this thing is minimized, then all the knowledge of what the algorithm should do has to be somehow included in that function. Good. And here basically we have a lot of things included. All the data goes in, our hypothesis goes in, so our assumption of what the patterns are, and our assumption of what is bad and good goes in. Basically by means of that square here, where we say smaller errors we don't care about, larger errors are really bad. So with this tiny function, we tell the learning algorithm a lot. Our assumptions, what is bad and what is good, all the data, it's everything in that function. Good. Intuition, how this loss function works. Let's quickly go over that. Our hypothesis, and to make it very intuitive, we pick out one of the parameters and just work with a single parameter, the gradient. We fix the y-axis intercept at 0. This makes our hypothesis function to be 0 plus theta 1x. 0 because we fixed it. So we just have one parameter, theta 1. Our cost function becomes this function here. Basically, the only thing that changed the last slide is we only have one parameter here. So it's a one-dimensional function that makes it easy to plot. And our goal is to minimize the function with respect to the parameter. just to really recap everything in order. Let's imagine for a moment these 3 data points are the 3 data points we have. And we have chosen for the moment as one of our first functions to evaluate the cost for this green function here, which is h of x with parameter 1, gradient 1. What is the cost of that? Basically, we just plug in the 1 here and do the math with this formula, which turns out the cost is 0. The cost is 0, which fits very well with our intuition. It goes through all the points. The error is 0. It works very nicely. So this cost function really captures our intuition that this is a perfect function for these 3 data points. And conversely, this plot that is not a plot of the hypothesis function, but a plot of the cost function, shows us a cost and error of 0 for the parameter 1. What happens if we choose a different cost a different hypothesis? For example, one with a parameter of 0.5, gradient of 0.5. Intuitively, it is less good than the other one. It doesn't go through any of the points. But what exactly is the cost? Of course, we do the same thing. Turns out the cost is 0.58, which in a plot is a point here. If you continue that game, hypothesis with a gradient of 0, intuitively even worse, leads to a higher cost, roughly 2.33, a point here. And if you would still continue that, we would see that the cost function in that case is a parabol, a hyperbole in 2 dimensions, which is exactly what you said. Our cost function is a quadratic function. A quadratic function looks somehow like this, and this has some very neat properties for optimization. Some of you may have taken the module on optimization. I don't know the content in detail, but I guess this kind of function is not talked too much about because it's so easy to optimize. For these kind of functions, you basically know where the minimum is. You could even analytically come up with the solution. You wouldn't need a step-by-step iterative algorithm to do it. It might still be good to do it iteratively, and we'll talk about it later. But this should give you the correspondence between different versions of your hypothesis in the X space and different cost values in the parameter space, where you've got parameter values. Okay, I assume this is basically fine for everyone, right? No rocket science here. Let's go back to 2 parameters. What becomes of a hyperbole if we are not in 2 but in 3D? It's still a hyperbole. It looks like that. Oh. It's still easy to optimize. It's still a convex function. Who is not aware of contour plots? Are you able to read these kind of things?
No.
Nope.
No.
So, if you imagine that thing, this is a shape like a salad bowl, right? This thing. If you would look at from above, this plot basically is doing exactly that. It's looking from above and showing you like on a map the hate lines. It's basically a 2D version of that plot. Again, let's do the same thing we did on the last slide for 1D, now in 2D. The example here is a little bit different. We have housing size of houses and the price of houses. These are the data points. You again want just to fit a straight line to it. What are shown here are different instances of the straight line and the corresponding points on the loss surface. Intuitively, this line is doing it quite well, and it has a point near the minimum value of the loss function. pretty much in the center of the bow. These here are all somehow bad, but we see with the plots on the loss surface that it's gradually becoming back. And this succession of, we have a line here and then we somehow start pulling it into a direction where it fits better, gives rise to the idea how in machine learning we usually optimize these kinds of loss functions. And that is the idea of gradient descent, of always going into the direction of the steepest descent. You basically know how it works. You have some starting value, typically randomly chosen, for example here, and what you do then is you calculate the gradients in all the directions of your axis, which are your parameters, and you go into the direction of the steepest descent. From here, it's definitely not to the direction of the top. You want to do descent, so it's probably somewhere in this direction. And you do this with some step size, and you iterate. What's the steepest descent in all the directions? Go into that direction. And you do that until you arrive at a minimum. Can you be sure that this is a global minimum? You can't. You just found a minimum, a local minimum. And it's very much dependent on where you started. If you start somewhere else, just a little bit next to it, it might be that you end up in a different local minimum. So that's a disadvantage of the method. An advantage is actually this thing does not rely on the function to be convex. You could use this optimization method for basically any kind of loss surface, which is why it is so famous for neural networks. Neural networks don't have a convex loss surface. The point that gives us hope that this algorithm works well in practice usually is that we assume that our cost surfaces are usually smooth. This is also an assumption we somehow have in neural networks. We say, okay, we know there are different local minima and we will always end up in different ones, but it will somehow be okay. It doesn't matter too much in which local minimum we end up with. Still, the question is, if in the example of the lecture today, we have a convex loss function, why do we want to do optimization using an iterative algorithm that is going stepwise? We could analytically come up with a solution. What would you say?
Gives also some information on how the function is outside of our minimum.
We can gather information about the shape of the function outside of the minimum. Yes, we could. But in case of our example, it's a convex function. We basically even know that. So we wouldn't need to gather information. Are there, do you know other reasons that could speak for the iterative solution in order to find a minimum? Also, where are we? Also, in the case where our function looks like that, why iterative? Yes?
To calculate the derivative is sometimes hard. Let's say.
Calculate derivatives, sometimes hard, yes, but we would need to calculate them in both, for both kinds of versions of the algorithm, for the iterative one and for the analytical solution. And yeah, I agree, sometimes it's hard to calculate. This is why we give it to TensorFlow somehow. Imagine it the following way. Here we see a loss function with two parameters, and our data points are a handful or two. It's very easy to do that analytically. If you have hundreds of thousands or millions or hundreds of millions of data points and thousands of dimensions, it becomes near to intractable to do it analytically. And even if it's possible to fit it into the RAM of a supercomputer, it might be much more easy to do it in a distributed fashion on some standard computers that just iterate over the data set in order to do it in one huge equation which you can solve analytically. So there are computational reasons for doing this stuff step by step, iteratively, with something like gradient descent, instead of calculating the minimum analytically, even of functions where we know we could, in principle, know where the minimum is. Plus, gradient descent is a general method. It just does not just work for our linear regression example. You can use the same thing for neural networks, which don't have a loss function like that. Good. Let's skip forward here. Let's look at the algorithm, and we're almost through already. What do we want to do if we want to implement that stepwise, look where the steepest descent, go a little bit in that direction, look again, iterate that? How would we implement that? Basically, we would have an infinite loop. In that loop, loop over all our parameters and calculate the new parameter value as the old parameter value minus, like adapting a little bit into the direction of the steepest descent. We calculate the derivative of the loss function with respect to the current parameter. We multiply this steep gradient with the step size for learning rate alpha, and we adapt our current parameter value a little bit based on the step size into that direction. We do this for every j, for every our parameters, calculate the new ones, store them away, and when we are finished, having done it for all the parameters, we copy the new values over the old. So we do simultaneous updates. That's basically important if you implement it from scratch. If you do something like this, you say new parameter value is old parameter value adapted a little bit into the direction of the step size, and you directly do the update. You will use the new value you calculated here already in the calculation for the next dimension, and this is wrong. It will not yield gradient descent. It will not yield a mathematically sound method. It will basically bring a bug into your training algorithm that you might not discover at first because it maybe gives you even better results, but it's not any more mathematically a valid method. It might give you better results in a specific training set, and so you use it, and in the next one it doesn't work at all, and you have no idea why. And your idea is because you implement in code a different formula than you have in pure math. In pure math, this is done simultaneously, so you have to implement it. Why highlight that? Basically, I highlight that to make you aware of that. Even when we said before, it's not about software development here, it's about coding stuff. The coding has to be done like with your eyes open and very much concentrated. The stuff we code usually has a correspondence in mathematical formulas that have correspondence and a root in theory that show why it works exactly that way and not in another way. And if you deviate from this in your coding, you end up with algorithms that actually don't work. In standard machine learning, like these kind of things, even in deep learning, we usually have very good libraries that encode the stuff okay-ish. I just talked to some colleagues at PwC. They said they had a good look at the scikit-learn library, which is a standard machine learning library of Python, and they didn't find a single algorithm without bugs. Like hard bugs, like bugs that make your model not work as good as it should. And this is a standard machine learning library of Python. I just talked to one of my PhD students who found a similar bug in a TensorFlow implementation of some code that should basically produce gradients for specific kinds of functions. So these kind of bugs are everywhere. It's quite okay even if they exist in normal machine learning. If you go to the field of reinforcement learning, which is, I would say, in terms of maturity, a little bit behind, most of the problems, I would say 80% of the problems fail, and most of them because of bugs. Because somebody reads the description in the paper, says, I code it, do an experiment, it doesn't work, maybe somebody else can make it work, I upload it on GitHub. Somebody else says, oh nice, it's on GitHub, I don't have to read the paper. Try it, work half a year on the thesis, doesn't work, bad results, and all because the code was bad. So these kind of things are really important to keep in mind. And when you are the one who is not using a tried and tested implementation where you know it's okay, of course then use it. But if you are the one who reads a paper and writes the first implementation for it, really check for these kind of things. Try to come up with simple examples that you can numerically go through even by hand and see, does my code do what my formula lets me expect. It's super, super, super important. Even if it sounds very basic and not very sophisticated. Good. Intuition behind the learning rate. The learning rate basically is a parameter that controls how fast you make progress. Of course, you just scale the gradient by the learning rate, meaning if you're farther away from your from your goal, if the gradient is larger, the steps will also adapt. But if the learning rate is small, you will do lots more steps than when the learning rate is big. Problem, if it is too small, you will not converge, it's just too slow. If it's too big, you might even diverge, even if you use the correct algorithm. So these things is what we usually call hyperparameters, and these are parameters that you self have to tune. Like your learning algorithm cares for the parameters, the thetas of your model, but you have to care for the parameters that control the optimization, the hyperparameters. Yes?
It's 1440.
Perfect. And we are almost through. Thank you. Eager minds could come up with the idea that why should the algorithm just care for the parameters and I should care for the hyperparameters? And if you think in that direction, you end up in the field of automated machine learning, which is very interesting. You apply machine learning to machine learning in order to set the hyperparameters directly, automatically, optimally, so that the algorithm that comes out of this finds the parameters optimally and automatically. That makes your brain a little bit dense and do funky things. It actually works very well. We just finished a milestone in a research project on that together with the company. And it really works nice, not on problems where it's generally unknown how it should be approached with machine learning, but on standard problems like the one we talked about. The way this company sold the project to their management was, you know, we had a very a consultant with a high salary who worked for a customer for 3 months in order to understand the problem, talk to everybody in order to get an understanding of the business side of the thing, have a good look at the data, try all the different methods and come up with a model that works really well. So it comes back to the central after 3 months, brings the data on a USB stick. They load the data into their thing they call the data science machine. It calculates for half an hour, comes up with a model that is within statistical fluctuations, same performance than what the consultant did in 3 months. For a standard problem, these things are like you have data about your customers and you want to predict sales next month or so. These things can be done. So you actually don't have as a human to tune the learning rates yourself. Actually, you can if you have lots of hardware. Of course, this costs compute. Let the computer do this as well. It's called automatic ML. Final thing, overview about everything we talked about. We talked about our representation. The representation is just the mathematical description of how our model looks like, which is a straight line now. We talked about the evaluation. How do we tell the learning algorithm if it's doing good or bad? What is optimized? It's basically the loss function. You can find the derivation of these equations, like here, of the two partial derivatives in the appendix for those who want to see how it's done. But that's basically a recap on what you learned in school, probably. And you have, for implementation reasons, everything written here. And we have the optimization, which is batch gradient, and you see the code here. Everything put together. This is what you need to do if you want to do gradient descent for linear regression completely from scratch, without any library, just pure Python code. You can basically take this and implement it in maybe 10 lines of code. You could do that, and in the next lab you can do that. You have the opportunity. I have provided you with a Python script that loads in this kind of data and also produces nice plots, hopefully nice plots. And there are free slots for you where you can fill in this kind of stuff. Even if you already know the method and everything, do this once, please, to do this translation process from math to code once for yourself and see how many bugs can I build into it. Very last anecdote from myself. I was writing the lab code for that when we were visiting my in-laws, and I actually thought, I will get up a little earlier, and before breakfast I quickly go into the office of my father-in-law and write that code, and I come down and we will have a nice weekend. And it turned out I got up at 7 in the morning or something like that. 2 o'clock in the afternoon I was still sitting on the desk and fixing my code because it had bugs. And because it's actually, even as a computer science professor, not so, or maybe because, I don't know. It's not so easy to write this kind of stuff bug-free from top to bottom. Okay, the bug was actually not in that formulas, but in the plotting stuff. But anyway, coding can become difficult, and it actually just needs exercise, especially for those of you who are not daily coding. It just needs exercise, so please use the chance to do something. So, we are through. I will not read that for you. Thank you very much for your co-laboring here, and see you next week, or until that.